I would I would be very happy to have the opportunity to visit someday in person when
yes, of course, please do. Yes, open invitation.
Yeah,
we'd
thank
love
you.
to have you here.
But we'll have to make do for now in this mode. Please interrupt at any time, ask questions. If you want to leave your video on so that I can see your faces of frustration when I say something you don't like, that would be a help. But so let me start with some basic questions or observations. So let's take a manifold. So M is some, let's say, hyperbolic manifold. And a very basic thing that people like to study is the length spectrum, or just the length set in this case. So this is the set of length of closed geodesics, where C is a closed geodesic on M. Or really the unit, okay, to have a geodesic, I need a unit tangent vector so that I can flow, but so M is some kind of manifold, whatever it is, and it has some closed geodesics, and maybe some complicated ones. Okay, and then we just take all their lengths, and that's this set L. And so a basic question is, what can we say about this set L? Is there anything meaningful that can be said? So as is pretty well known, the set of lengths is very closely related to the set of traces of the fundamental group. So let pi 1 of M be some group gamma, which is a discrete group of isometries of whatever the universal cover is. It'll say an N manifold. So this is the set of traces of gamma in gamma, and of course traces, because this is invariant under conjugation and so on. And of course only the hyperbolic traces have this correspondence, but regardless, there's this sort of simple formula relating the two things. And so trying to understand the set of lengths of closed geodesics is very closely related to trying to understand the set of traces of a given manifold. So let's just do a couple of warm-up examples. So this is warm-up, just to see what kind of things we might be able to ask or say about anything. So warm-up 1, let's think about the 2, 3 infinity Heka triangle group. Okay, so this is the group, let's say, inversion in the imaginary axis, inversion in the x equals 1/2 plane, and inversion in the unit circle. So this is your 2, 3 infinity Heka triangle group, and of course this is a double cover of the modular group SL2Z. And so one might ask, well, what is the set of traces of this manifold H mod SL2Z? H mod, let's call this gamma. Okay, so let's see if people are awake. I guess it's the evening there, it's the morning here. Let's see if I'm awake. What is the set of traces? What can we say about the set of traces of SL2Z? It's too simple a question, so it just requires.
Everything can be a trace, surely.
Not everything, exactly. All the integers, of course, because all you have to do to understand what element is in SL2Z, all you have to do is solve the equation, A, B, C, D are integers, and AD minus BC equals 1. And you just take whatever trace, whatever number T you want to be a trace, you write it in any way you want as A plus D, and then you have to solve, given A and D, you just have to solve BC equals, what is it, AD minus 1 or something. And in other words, B and C are divisors of AD minus 1. So it's extremely easy to solve this equation, and it's an arithmetic group. So you get all the points that you would from this equation, all the integer points. And so the traces are everything, and there's no question on the modular surface, we understand everything about the set of lengths because we understand everything about the set of traces. By the way, even with multiplicity, we understand quite a lot. So there's a paper of Chawla, I think Cowles and Cowles from the 80s that studies the class number. So this is the kind of a Hurwitz type class number. H of t is the number of not just traces, right? It's really not traces. It's really not traces of elements that gives you lengths. It's that closed geodesics correspond to hyperbolic conjugacy classes, and conjugacy classes are trace invariant. So this is the number of conjugacy classes of elements in the group with trace being this given number t. And what Chawla observes, what these three authors observe, is that this is basically the class number, the classical class number. This is the Gauss class number, if you like, class number of binary quadratic forms with discriminant t squared minus 4. Now t squared minus 4, this is a positive discriminant, and we know exactly what the regulator is. We can solve the Pell equation because the discriminant is given to us as a solution to a Pell equation. Typically, that's the difficult part in computing the class number, and so it's really very easy to see that this class number will be as large as possible, and the largest class number is around square root. So the class number will be the square root of t squared. So it's t to the, let's just be crude, 1 plus little o1. Okay, and so if you sort of think about what these class numbers look like, so here's t and here's h of t, it's basically growing linear. And of course, that'll be consistent with the fact, so this is a typical traces multiplicity. And it's not multiplicity in the sense of elements in the matrix, it's multiplicity in the sense of conjugacy classes. But of course, you can also, if you have such an element, then you can find A and D so that typically you'll have an element of that norm ball with having that trace. In particular, let's compare this, compare to the number of elements in SL2Z in a ball. So take your favorite, fix some Archimedean norm on balls in R4 or something. And this will grow roughly at the, what's the growth exponent of this? I'm sure everyone on this call knows. But everyone's being shy.
With 3?
Oh, 3 is a great guess. 3 is a great guess. 3 is indeed the size if we look in SL2 Z mod P, Z. This is of size P cubed, give or take, lower order things. And that's because it's one equation, but it's one quadratic equation. So actually, if you think about it, once you fix A and D, which you have n squared choices if A and D are of size n, then B and C is a divisor sum. And so there's n to the epsilon choices for B and C at most. So it's actually, it grows like n squared. Okay. So again, any questions, please stop me, slow me down, which by the way is completely consistent with the fact that the class group grows like T. So the total number of traces, if you add them up to some capital N, will grow like n squared. Okay. Any questions on this warm-up example before we get to something a little more elaborate? So far, so good?
Yes, very good.
Okay. So let's try something related. Instead of 2, 3 infinity, let's try 2, 5 infinity. So what happens to the Heka 2, 5 infinity group? So the picture is exactly the same. The 2, well, and the infinity are accomplished by inverting in the, the 2 and the, well, the 2 is accomplished by inverting, let's say, in the unit circle and in the y-axis. So that gives us a right angle. To get infinity, I need a parallel line. To get a pi over 5, so if I want this angle to be pi over 5, it turns out that I have to take here the golden mean, or maybe half of the golden mean. So phi is the golden mean, 1 plus root 5 over 2. And so this is the classical Heka 5 triangle group. And just like SL2Z, so SL2Z, let me do a little aside. SL2Z, or it's really PSL2Z, but I'll drop the P's everywhere, is generated by inversion in the unit circle and translation by 1. That's this unipotent element is translation by 1. Here we have translation by phi. So this group, or at least its orientation preserving double cover, is generated just like SL2Z by inversion in the unit circle. So now I'm sort of doubling things. And translation by phi. Okay. Well, so what does that mean? That means that this group is a subgroup of SL2. It's all matrices, 2 by 2 matrices with determinant 1. But the coefficients are now not in Z, they're in Z adjoin phi. But Z adjoin phi does not act discretely on the upper half plane. It does act discretely on 2 copies of the upper half plane, or rather, it's better to act in the homogeneous space. So it acts on 2 copies of SL2R, in the first by the identity action, and then the second, well, I didn't tell you which phi or phi bar. So you make the Galois conjugate. I did tell you which phi, because we have to have a real embedding. These are actual lengths that we're measuring. So there's the identity embedding, and then this is the Galois conjugate embedding. So there's this diagonal action where SL2 Z adjoin phi becomes a lattice in the product of 2 SL2s. And the other factor is a non-compact. And so this is a nice arithmetic lattice. And this gamma is a quintessential example of a non-arithmetic lattice because it's already a lattice in the first factor, and the second factor is non-compact. So this is a non-arithmetic lattice. But okay, in SL2, in SL2R, SO21, you can have really non-arithmetic lattices. It is a lattice. It is a finite volume quotient. This triangle has finite area, but it's sub-arithmetic. Sub-arithmetic because it's contained in an arithmetic group. So at least we know something about its traces. You could take some, you could take something with really, I mean, there's a whole Teichmuller space in which you can deform these lattices and get something really crazy. But at least we know that the trace set of gamma will be contained in the trace set of this arithmetic group. And the trace set of this arithmetic group, just as before, is the full ring of integers. So this is the full ring of integers, Z adjoin phi. Now, just as before, this fact has nothing to do with SL2Z. This is true for any lattice. So the number of elements in gamma in a ball of size n is still n squared, just because that's what is true for any lattice in SL2R. But what is going on with these class numbers? So these class numbers, T is now an element in this quadratic ring. And what is the multiplicity? So let's call this H gamma of T. Again, this is the number of conjugacy classes in this new group gamma, with a trace of gamma being this given element of the ring Z adjoin phi. Of course, I can think about this as Z plus Z times phi. And so I like to think of the...
Alex, Venki here. May I interrupt, please?
Please. Hi, Venki. How are you?
I'm doing fine. Thank you. See, when you say T lies in Z phi, it's actually an integer. Is that what the class number? What does it mean, class number, in that sense? Is it a...
So I'm just defining this object. In fact, it's a class number of Dirichlet forms.
Okay, sorry. Yeah. Okay.
Yeah. But if you want to think about it in just the most basic terms, you have some group. You can take conjugacy classes in that group, and it'll have some traces, and those traces, because the elements all lie in Z adjoin phi, the traces will all lie in Z adjoin phi.
Okay.
And so let's group the conjugacy classes by whatever the trace happens to be, and let's count how many such conjugacy classes there are.
Okay.
Does that make sense?
Yeah. Thank you.
And so if we plot the sort of the z part in this direction and the z phi part in this direction, we can ask, what is h gamma of a given t? So t is happening in this plane. And then what is the graph of what we're seeing? So what might you expect? Well, the number of points, so the number of t in this ring in a ball of size n. Let's see if people are awake. So I have a quadratic ring. How many t's will I have in some ball?
Infinite.
In a fixed ball, in a ball of radius n. Just crudely. I have like z squared. How many integer points are in a?
Okay, n to the 4 maybe.
It would be to the 4 if I had two t's, it would be to the 4. But it's just z cross z. So it's just a lattice. It's just a square lattice looking thing. So it's just n squared. So it's n squared roughly. And so here's the rub. Here's where it gets a little complicated. The number of points, the number of traces, is the number of possible traces is n squared, and the total number of points is also n squared. And so one of two things might be happening. It might be so either every trace is represented a bounded number of times. So I'm plotting h gamma of t. So above every single point here is a height 1 multiplicity. Or if that's not true, then very few, let's say it could be that 0% of the traces are represented, but the ones that are represented, in some growing number of classes. Because the total number of classes still has to add up to n squared. But now the total number of points on which those traces land is also n squared. And so what's going on? Are they becoming equidistributed? And every trace sees roughly the same number of conjugacy classes? Or are some traces not represented and other traces are overrepresented? Well, it's complicated, but it turns out, so this is a theorem of Kurt McMullen from last year. It turns out that this is what happens. In other words, if we look at the number of traces in a ball, so the number of t in the ring z adjoint phi in a ball, such that this class number is non-zero, this is little o of n squared. So 0% of the traces are represented. 100% of the traces have 0 representation, and then some very few guys must have some growing representation numbers so that the total number of points adds up to n squared.
May I interrupt once more? So
Please,
this gamma is a thin subgroup of this SL2Z22. That's where
right. So in terms of the definition of thin group, you're absolutely right, because the Zariski closure of this is this SL2 over this ring.
Mm-hmm.
So it is a thin group, even though it's a lattice in SL2R, it is a thin group.
Okay.
Yeah, this is where the nomenclature between thin and lattice is where you can see this distinction. So I would call this thin.
Okay.
Even though it's a lattice in SL2R, this sub-arithmeticity means that we can think of it as a thin subgroup of this arithmetic group. Yeah.
So if you had replaced gamma by the full arithmetic group, then the count would change n to the 4 or something. That's what
Exactly.
That's
exactly.
Okay.
Here the count is n to the 4 for exactly that reason. Yeah.
Yeah. So thanks very much. Sorry.
Yeah, my pleasure. Please continue asking anytime. Yeah. So actually, let me make Benki's point. Let me write it here. Note. Let's just make this explicit. Gamma is a thin group, thin subgroup of the arithmetic group z adjoint phi. And if we look at the traces of SL2 z adjoint phi, we would get the full ring, Z adjoint phi, and the number of points, in this group, SL2 Z adjoint phi in a ball, is n to the 4. Exactly as Venki said. Here, the number of points is still n squared. So the expected multiplicity, of a trace, I don't know that anyone has actually done this, but I don't think it would be that hard. I would expect this to be roughly t squared. Or I have to take some kind of norm of t squared now. An algebraic norm would probably be better. Okay. So yeah, that's just an aside. That probably isn't too hard to prove, but I don't know that it's in the literature. It probably follows by similar methods to what Chawla was doing previously. Great. Okay, any questions? Any more questions so far? Okay. Example 3, let's just go one step farther. Let's look at the Heka triangle 2, 7, infinity. Okay, so same exact idea. Same exact picture. I have inversion in the unit circle. I have inversion across the y-axis. And now I come out over here to cosine of pi over 7, I guess a half cosine of pi over 7, wherever this point is, so that this angle is pi over 7. And so now I have a 2, 7 infinity group. Anybody know what the degree extension of cosine of pi over 7 is?
3, I guess.
Yeah, 3. Yeah, it's a cubic. So this is a cubic extension. So there's an orientation preserving subgroup here, which is generated by, as always, inversion in the unit circle, and then translation by cosine of pi over 7. The number of elements of gamma in a ball is it's a lattice, so it's still n squared. There's still n squared points in this group in a ball in R4, but the number of values of, so O is now the cubic ring. O is the cubic extension. Let's call it O. The number of points in this cubic ring is n cubed. And so there's no chance whatsoever, no chance of of understanding very concretely what the possible traces are of understanding the trace set of gamma in terms of elements of O. In terms of O, the number of elements of O in a ball is just way, way bigger than the number of elements gamma can produce in a ball. Okay, so it's really a thin set. It's here where we had a chance. It's here where we had a chance of producing the same number, and Kurt's theorem says that in fact, no, that this fails. Okay, so so let me introduce some notation of what I would like to say. So other obstructions to, let me give you just 2 more obstructions, further obstructions to a given number to understanding the trace set. Well, it's not really to our understanding, but to possible values of the trace set, understanding of the trace set. So let's go back to, right. So I will definitely want to restrict to groups that are subarithmetic. So one is that gamma I want to be subarithmetic, contained in an arithmetic group, so that there's a maximal order generated by the traces of T will be some maximal order O, maybe it's a ring of integers of something of some arithmetic group. So there's an arithmetic group that contains gamma, and so its trace set will be some full ring of integers, and the traces of gamma, of course, will be contained there. So one is that we want this gamma to be subarithmetic. We have a chance at understanding this trace set. 2 is this phenomenon above. So we want the growth exponent critical exponent, but let's just say, let's call it the growth exponent of gamma. Let's say alpha is the growth exponent of gamma, i.e. the number of elements in gamma in a ball is n to the alpha plus little o1. Such a thing always exists. It's the abscisive convergence of the Poincare series for gamma. So there's always some number. If we compare this growth exponent, it should be larger than the growth exponent of the rank of this ring. So what we saw before was in the last case of 2, 7 infinity, the growth exponent was 2 and the rank of the ring is 3. And so there's no hope of having some kind of local global principle for the traces. So we need the growth exponent to exceed the rank. Does this make sense? Any questions so far?
Well, it makes sense.
Yeah. Another thing that might happen, so already there may be local obstructions. So for a very simple example, we can take the principal congruence groups of level Q. So this is the kernel of the map from SL2Z to SL2Q. Okay, in other words, it's the matrices in SL2Z that are the identity mod Q. These are your typical lattices, but of course, so these are matrices. These are matrices A, B, C, D that are congruent to 1, 0, 0, 1 mod Q. And the traces, all of these traces must be 2. So the traces of gamma Q are all congruent to 2 mod Q. Okay, so yes, the trace set, the trace set generates the full ring Z, but you won't see all traces. There's a local obstruction. Okay, so there may be local obstructions that we have to be aware of for trying to formulate what it would mean to understand a trace set like this. And a fourth obstruction is that you can always kill the systole. So the systole may disappear in covers. Disappear in a cover. In other words, whatever my manifold, if my manifold looks like something, and I have some very short, the systole is the length of the shortest closed geodesic, the shortest length of a closed geodesic. So I have some systole here, and then if I just take a little cover, all of a sudden that shortest length may no longer, this was a closed geodesic. When I take a cover, it's no longer a closed geodesic, and now maybe it's the lift is a much longer curve. Okay, so there may be, in other words, maybe you can think of this, if you like, as an Archimedean obstruction. Archimedean obstruction for small traces. And the question is, beyond these kind of obvious obstructions, perhaps there's a local to global principle. So let me try to formulate such a thing. So any questions so far?
Okay, I mean, I would like to ask, when you say trace, actually you mean trace in Z root, sorry, in the ring of integers, so the number field, not in the thing, right? So when you say shortest geodesic, what does this mean? Because it's related, it's only in one Archimedean place, is it not?
Exactly. So the group already has an Archimedean embedding. It comes with an embedding into R so that we can see the geometry, right? It's actually acting on hyperbolic space. So it may have other embeddings, and the traces might be, we can recognize these traces as elements of some ring, but actually they're also real numbers at the same time. So in other words, there's always a fixed embedding into R,
Okay.
because these are real hyperbolic manifolds.
Okay. Thanks. Thank you.
Does that make sense? So there really is some manifold, and there really is some unit tangent vector that when you flow along that tangent vector closes up, and then that will be the length that I'm thinking of. But that might be an element of Z adjoin root 5, and it has a Galois conjugate that you don't see on the level of the real group.
Okay.
Other questions? So okay, so in this formulation, and by the way, because there may be local obstructions, I'm going to define. Let me make this definition here. So definition: an element T of this ring O is admissible if for every ideal in O, T is in the set of traces of gamma mod the ideal. So that's what it means. That's what admissibility means. I want to pass all these local obstructions. And in practice, this is something that's really not hard to establish, because even though this may be a thin group, it's a Zariski dense group. Well, if it's a Zariski dense group, then we have strong approximation, and we can sort of understand what these reductions modulo the various ideals look like. So actually, admissibility is not a difficult thing to ascertain. Okay, and so so let me make a definition. We say that gamma length saturates if every element T of the ring generated by the traces of gamma that is admissible. So again, that means passing all these local obstructions, and sufficiently large, and the norm is sufficiently large. So that's getting away from the fact that you might have you don't know where the length spectrum might begin. Every admissible sufficiently large trace actually is if for every T that is admissible and sufficiently large, T is actually globally represented. T is actually a trace in gamma. Okay, and of course, to have any chance of this, we need, just to remind you, we need that the growth exponent of gamma exceeds the rank of the order. That's a necessary condition for length saturation. And that may or may not hold. So let me give you a second definition. We say gamma asymptotically length saturates. Asymptotically length saturates if this holds for a subset of traces of density 1. In other words, if the number of traces in the group in a ball of size n divided by the number of traces that are admissible, traces in the in this order in a ball of size n that are admissible, if this ratio goes to 1 as n goes to infinity. Okay, then we say gamma asymptotically length saturates. Do these two definitions make sense?
Yes.
So, so let me tell you a theorem. So the first step towards understanding something like this is joint work with Xin Zhang, I guess 21. Says the following: let gamma be a Zariski dense subgroup of the modular group. the Zariski dense subgroup of SL2Z, PSL2Z, and punctured, and assume gamma has a parabolic. Parabolic element. Okay, so it's non-uniform, non-convex co-compact. I don't know what you want to call this. Non-uniform. It doesn't have to be a lattice, just Zariski dense group, and it has a parabolic element. Then gamma asymptotically length saturates. Asymptotically length saturates. Okay, so let me just make a few remarks. So, okay, it's a subgroup of SL2Z. It's Zariski dense. So the remarks. The order here is just Z. The rank of O is 1. And so we need the growth exponent. Alpha is the growth exponent, critical exponent. It's not the, well, let's just call it the growth exponent. There's a reason I'm not saying critical exponent. The growth exponent alpha needs to be bigger than 1. And what is the growth exponent? The growth exponent in this case is twice the Hausdorff dimension of the limit set of gamma, it turns out. So the number of points in a growing ball in gamma is twice the Hausdorff dimension. So the Hausdorff dimension is often what's called the critical exponent. So that's why I'm calling alpha the growth exponent. So we need this growth exponent to be bigger than 1. In other words, we need the Hausdorff dimension of the limit set to be bigger than 1/2. But I didn't say anything about the Hausdorff dimension in this theorem. So the remark is that if you have a parabolic element and you're Zariski dense, so remark, this is a basic fact, Zariski dense and non-uniform implies that the Hausdorff dimension of the limit set exceeds 1/2. This is an easy counting statement. Okay, that's one thing. Another remark is that we can take that there is no further restriction on the Hausdorff dimension. So maybe I should mention the relation to some related work where this Hausdorff dimension becomes very highly relevant. Let's see. Is it 45 minutes? How long do I go? Or 50 or an hour?
It's an hour. It's an hour.
It's an hour. Okay, good. Oh, then we have the luxury of time. So then let me try to tell you something about where this comes from. Some more remarks. So compare to the following conjecture. So McMullen calls this the classical arithmetic chaos conjecture. Classical arithmetic chaos, as opposed to quantum chaos, arithmetic chaos conjecture of McMullen from a few years ago now. Don't quote me on this. I'm just going to put a number there, which says the following. So let me give you a kind of a special case. If you look at the set of continued fractions, A0, A1 up to AL, periodic continued fractions. So this means A0 plus 1 over A1 plus 1 over A2 and so on, and then periodized. So this will be a quadratic irrational. And I want to ask, when does this lie in the field Q adjoin root 5, let's say? And I want to restrict to all the partial quotients, all these partial quotients, AJ being, let's say, 1 or 2. 1 or 2. McMullen's conjecture, so we can look at the set of periodic continued fractions using 1s and 2s, and if you just restrict to the ones of length L that lie in Q adjoin root 5, well, how many total points are there? If we don't restrict to, if we don't consider this number field restriction, the A's are 1 or 2, and there's L of them, or L plus 1, whatever. So the number of points is 2 to the L. So there's an exponentially growing number of points. And the question is, when I restrict to lying in a particular field like Q adjoin root 5, the only reason I say Q adjoin root 5 is at least I know one element. 1, 1, 1, 1, 1, 1, 1 will be the golden mean, which will lie in Q adjoin root 5. So if I restrict to this set Q adjoin root 5, does the number of points grow exponentially? So, at least some constant, does the number of points, hello, okay, does this number of points grow at least like some constant to the L as L goes to infinity? So this, this is the positive entropy of the set of low-lying closed geodesics on the modular surface restricted to lie in a particular field. So that's sort of where this interest came from. So some remarks. This bound on right. So it doesn't have to be 1 and 2. You can take 1, 2, 3 up to 100 or something if you're interested. It doesn't really. This is sort of the simplest instance of this conjecture, but he conjectured something more general in that it doesn't have to be Q adjoin root 5, and more flexible in that it doesn't have to be 1 and 2. You can allow larger alphabets. So the remark is that the growth exponent of this the Hausdorff dimension of the set of all continued fractions, not periodic ones, but all of them with digits bounded by 2. This Hausdorff dimension has been studied for a long time, and it's something like 0.531, something like this. We know 100 decimal places of it. This is like the very, very badly approximable numbers. And this number 0.531, it's bigger than a half. Okay, so that's one remark. It'll be relevant in a minute. So another remark is that each such number. So again, this is some number with the AJs bounded by something. Doesn't have to be 2, but let's just call it 2, just for definitiveness. Corresponds to a closed geodesic on the modular surface H mod SL2Z, which is low-lying. So if I draw a picture of the standard fundamental domain for SL2Z, what does it mean to be low-lying? Well, the fact, what's the connection? This is some number, let's call it beta. So beta is some real quadratic number, and it has a Galois conjugate beta bar. And if you connect beta to beta bar by a geodesic, this will actually be a closed geodesic. This will close up in the quotient and come back to where it started. And the fact that all of the partial quotients, you see the distance that you reach into the cusp is controlled by the size of the partial quotients of the continued fraction expansion of beta. And so closing down this size of the partial quotients amounts to cutting off the cusp and considering only partial quotients that are low-lying, only considering closed geodesics that are low-lying. And the question is, okay, you can make low-lying closed geodesics, but can you simultaneously control the number field over which they lie? So we can control the geometry, we can separately control the arithmetic. Can we simultaneously control the geometry and the arithmetic? This is the type of question that Kurt was getting at. Really, he was studying higher rank rigidity phenomenon and showing just how badly those higher rank rigidity phenomena would fail in rank 1. But that's maybe another discussion for another time. So this was his conjecture, and this is still not known. In fact, it's not even known that using 1s and 2s, you will have infinitely many distinct, not just the golden mean partial quotients here. So I think currently we know something like 20 numbers that lie in this set, with L going also out to 20 or something, maybe larger, 50, I don't remember what people have done. So it's rather brave to conjecture that it will grow exponentially when you've looked out at such a large numerical sample and found 20 of these very low-lying closed geodesics. But I'll give you a conjecture, a related conjecture that maybe supports Kurt's conjecture. So a reformulation. So Bergan and I gave a reformulation of Kurt's conjecture a few years ago. I don't know what to put here. I'll just put a number. The reformulation is the following. If you look, so there's a simple observation, which is that beta or the number A0, A1 up to AL lies in Q adjoin root D, if and only if, when you take the matrix product A0, 1, 1, 0, A1, 1, 1, 0, and so on, AL, 1, 1, 0. If you multiply all these matrices, this matrix has, let's see, trace squared minus 4, trace squared of this thing minus 4 has square free part D. So let me call this is equal to some other square times D. Okay, if D is a fundamental discriminant, if D is the discriminant of this quadratic ring. So what does that mean? If you understand the trace set of words generated by matrices like this, then you can sort of understand what number fields the corresponding closed geodesics will lie over. And so we formulated this conjecture. This is a local global conjecture in a sense. Local global conjecture, this is again with Bergan from a few years ago, says the following. You consider, let gamma, let's call it gamma A, be the semigroup generated by matrices A110, where the A's are all bounded by big A. Let's say, you could think of big A as being 2 or something. And I only want the semigroup. I don't want the group generated by these, no inverses. So I just want to take words in these matrices. So that's this set. And the conjecture is not only, and by the way, so the number of points in gamma in a ball is of order, again, I'm being crude, n to the twice this Hausdorff dimension. Okay, so I'll make that observation. Then every, let's say, for all t of order n, if I look at how many matrices there are in gamma A with trace of gamma equal to t, this should be at least t to some positive exponent. And in fact, that exponent, well, let me just say it's t to some positive exponent. So then there exists some positive eta, so that for all t of order n, the number of points is at least, I guess I don't need this order. I could say n, okay, let's do it like this. In a ball of size n is n to the eta. Let's be a little crude. It's basically saying the same thing. The number of points in this semigroup where the trace is exactly equal to some given number t is t to the eta. And eta, we even conjecture that we know what eta is, twice delta minus 1. So again, what is this saying? The total number of points that we have in gamma in a ball of size n is n to the 2 delta. And what this conjecture is saying is that there should be no conspiracy among those, so that the number of points in hitting a particular trace is the total number of points divided by the number of traces in this range. And so this conjecture is still wide open. We still don't even know that a positive proportion of traces is represented. But our theorem is that this local global conjecture implies McMullen's conjecture. So if you understand everything about the traces, including this multiplicity, then so maybe you'll take that as evidence that this arithmetic chaos conjecture is true. Now, this still, as I said, is very much wide open. This 2 delta minus 1, the smallest value of A is A equals 2. If A is equal to 1, then you just have a single matrix and the group isn't, it's just, it's not Zariski dense. So if A is at least 2, as I said before, this Hausdorff dimension is bigger than a half. This Hausdorff dimension. And so delta, twice delta minus 1 is positive. So Now, so the conjecture is completely wide open. So not even today, not even a positive proportion of integers, positive proportion of traces is known. And we're saying not only is every trace represented, but every trace is represented exponentially many times, or at least in this formulation, it's polynomially many times. There's a related conjecture, which is Zaremba's conjecture, where one can say something more. So there's a related conjecture, which is due to Zaremba conjecture. It's still a wide open conjecture, is that there exists some A, maybe A equals 5 is enough, such that if you look not at the traces, such that if you look at the linear map that takes A, B, C, D, not to A plus D, but just to A, for example, if you look at the 1, 1 entry of the matrices, such that for L equals this, the values of this form on this same semigroup achieve all natural numbers. So every natural number arises as the 1, 1 entry of this group. And this is related to all kinds of fascinating things that, again, I don't have time to say anything about. But in this case, one can prove a positive proportion. In fact, one can prove density 1. So this is what Bergan and I proved some years ago. This, I think, actually, I do know the date is 14, is the analog of asymptotic length saturation. The number of elements of L of gamma A in a ball of size n over n goes to 1 as n goes to infinity. So 100% of the actual values that could arise do, which is of course very far from, and this is as long as the Hausdorff dimension is sufficiently close to some number, and this number people have whittled down. Our initial number was something like 0.9, and people have made it now 0.8 maybe, but it's still very far from the truth, which is which the truth should be a half. So so the remark is we don't know in the setting of this semigroup that a positive proportion of traces arises. In Zaremba's conjecture, where we can prove a positive proportion, we can't, we're nowhere near the truth in terms of the allowable Hausdorff dimension being as small as a half. And in this theorem, the Hausdorff dimension can be arbitrarily close to a half, as small as you like, and we're able to produce 100% of the traces that should arise. Of course, we're giving ourselves a parabolic element with which to work, whereas this semigroup that motivated these questions does not have any parabolics. So, all right, in 4 minutes, I can say a little bit about what goes into the proof, but maybe I should pause for a minute just to see if there are questions about what we just discussed.
So in particular, these groups gamma can be indiscrete, right? I mean, so.
Let's see, which ones? The ones in this local global conjecture or before?
No, before in the statement of the theorem, or
in the statement of the theorem, I'm assuming that there are subgroups of SL2Z.
Oh, sorry. Okay, I see.
Yeah.
Okay.
And in fact, they always have to be discrete because they're going to be the fundamental domain, the fundamental group of some manifold.
Ah, right.
They're always discrete subgroups as subgroups of isometries of hyperbolic n space for some n.
Oh, I see. Okay, sorry. Thanks.
Yeah, thanks. Other questions?
Maybe on that note, Alex, so here you are saying alpha is a growth exponent, but this is really not the critical exponent, right? Because the critical exponent is equal to the Hausdorff dimension.
Exactly, exactly. What I'm calling the growth exponent, it means, by this I mean, how many elements are there in a ball, in an Archimedean ball of size n? So I want this to be n to the alpha, roughly, right? And you're exactly right that this is the critical exponent or the Hausdorff dimension critical. That's why I'm not calling it the critical exponent. Yeah. So the critical exponent can be as small as a half. which makes the growth exponent of the group 1, at least 1, which means you have a chance. If you had fewer than n to the 1 elements, if you had n to the 0.9 elements in the group, those n to the 0.9 elements can't produce all the traces from 1 to n, because the number of traces is n to the 1. So there would be no hope if we didn't have more points in the group to produce the traces that we're looking for. And in this case, we can go all the way down to the limit of that requirement, as opposed to Zaremba, where as long as we have some much larger growth exponent, then we can produce points. So that was those were the two distinctions I wanted to make. Well, okay, I have 1 minute left. Let me just say a word on the proof. A word on the proof. So we use the orbital circle method. Orbital circle method, which is just the classical circle method, but applied to the context of orbits of group actions. And well, there are always two ingredients in the circle method. One is going to be exponential sums, methods of exponential sums and cancellation and bilinear forms. This is what's going into the minor arcs, if you know what that is. If not, I'm almost done. And for the major arcs, there's something very strange that happens. We face, this is something that I've never seen before in the major arcs. In the major arcs, what we face is very short sums. So the singular series, there's something called a singular series. And typically it is a very short sum, but it's a short sum that's absolutely convergent. Here it's a very short sum of something that's not absolutely convergent. It's a very short sum that's trying to be an L function at 1 of some quadratic character. And L functions at 1, you can approximate by very short sums under GRH. And I didn't say anything about assuming the Riemann hypothesis in the theorem was unconditional. And the other thing is these L1 chi's, we need them to be, it's the major arc supposed to be the main term. We need this to be, so if this has conductor, let's call it n, we need this, we need lower bounds for this L function of order like n to the minus epsilon, which we get from Ziegel's theorem, which makes this bound ineffective, which would make this ineffective. I didn't mention effectivity, but our result actually is effective. So why did I not mention, so this needs GRH, and I didn't mention GRH and I didn't mention ineffectivity. It's because I only stated we can only get the minor arcs, not individually, but on average, which is why we have asymptotic length saturation and not full length saturation. But because we are already averaging, you can get this short sum to look like an L function on average without using GRH. And Ziegel's theorem, you can also prove if you only want it on average, you can remove the ineffectivity. So because we're averaging already for the minor arcs, we may as well also average on the major arcs to make the statement unconditional and effective. And so these were some new ingredients that I hadn't seen before in the circle method in general, that as far as I know only arise in this orbital setting. So, okay, if that didn't make any sense, I'm done, and thank you for your time.
Let's thank Alex for a lovely talk. So Alex,